Hello, everybody. Welcome to another live lesson. Today's live lesson is going to be Cipher Solvers, Adventures in Geometry. So this is a pretty cool lesson because basically, if you've ever watched movies like, Dan Brown's books, the Da Vinci Code, or any kind of code-breaking movie, I think National Treasure is another good one. Nicolas Cage was in that one. Basically, the characters go through all of these sorts of adventures where they find clues, they have to figure out what the clue means, and that usually leads to another clue. And you never know when you're actually going to make it to the thing that you're trying to look for. Well, we're doing that today with mathematics and geometry, and our presenter, Curtis Brown, was one of the lead authors on this activity, and I think he's going to walk you through it. We only have an hour, but I think that'll be enough time to kind of get the gist. And before we start, just want to say thank you to all of you students, all the teachers, parents, everybody that's been involved, all of us who have been involved in sort of this COVID-19 crisis at the educational level. It's presented some unique challenges, to say the least. And so we're hoping that maybe we can provide a little bit of a distraction, a useful distraction, and help you apply some of the math knowledge that you've accumulated over the year, and sort of a fun and fictional sort of a way. So think about being in a movie yourself. We're in this movie together, and we're going to try to solve the clues, and Curtis is going to lead us through that. So with that, I want to go ahead and introduce you to Curtis Brown. Curtis has been at TI for a number of years. He was a math educator. Like I said, he co-wrote this activity amongst many others. And with that, I'm going to turn it over to Curtis.
All right. Well, thank you, Eric. Super excited to be here this afternoon and leading us through this activity, trying to get this cipher solved. Hopefully you guys have a little bit of fun this afternoon. We are going to do some algebra and some geometry in here. So if you want to follow along, I think it'd be a great idea to have kind of a piece of scrap paper there next to you, and maybe a pencil. It'd be ideal if you had the calculator with you, but I know that's probably beyond. So let's just go with scrap paper and get things going. So we do have a few shout outs to go for. So I'll do that. I have one there. There's a big group from Alaska and from Alabama, and Miss Howington's class. That's awesome. So I'm going to go ahead and I'm going to share my screen here, and we'll get started with this lesson. So I'm going to just get us going. There we go. So this lesson is one from our STEM Behind Hollywood series of activities that we have on the TI website. And I wanted to just point out before we get into the lesson itself that one of the key consultants on this activity was a man named Martin Strauss, Dr. Martin Strauss. He's a professor at the University of Michigan, and he's also a consultant for the National Academy of Sciences Science and Entertainment Exchange. And so he was able to work with us on this activity and give us some ideas on ways we could integrate some of these ciphers into the activity. So I'll be mentioning different things that he pointed out to us and kind of gave us suggestions early on. But the key quote, and I think this will be important for us today, is that it is important to think about the important advances in math and science, computer science, that come from us just playing and exploring and doing some of these things. So that's what we're going to do today. So let's go ahead and get started. So here's the main page of the activity. We land on the page of the activity. It's called Cipher Solvers. We're going to be using the TI-Nspire today, but if you have a TI-84 plus CE, you can also do this activity. It's certainly available for that, and we've written it. It'll work pretty much the same way. So day one, a strange message. Allison and Bobby find an old chest in the attic of a family farmhouse, and it was a book that they'd never seen before, titled The Raven and Other Poems. And if you guys know the author of that, I'd encourage you to put that in the chats right now. I'd love to see that come through. But Allison and Bobby were names that we chose actually when we were doing this activity. because Martin Strauss was telling us about how oftentimes when they're modeling these different kinds of ciphers and exchanges and things, that they will have a person A and a person B. So actually, we didn't just choose them because Allison was going to be on this podcast hosting it today. We chose them because person A and person B seem to make some sense. So that's where we're at. So here's the letter. Here's the letter that they found. It says, "Dearest Agnes, the cookies were splendid. Would you accompany to the fall dance? If you agree to this proposal, I will arrive at 6:15 to escort you to the coach." Now, most of you guys probably noticed that what I was saying and what you were reading probably didn't match up. Bobby noticed that too. What language is this? I don't know, but I do know who will. And conveniently, Allison's mom happens to be a cryptographer for the CIA. So, you know, I mean, when you're in Hollywood and you can make these things up, people can have any job they like. And so in this case, we have a cryptographer who happens to be Allison's mom, which is fantastic. So they noticed several misspelled words. Anybody check out those misspelled words in that letter? Eric, I think you probably called out a couple of them. Agree looks like it's messed up.
I think this and escort.
Escort. All of those seem to be messed up just a little bit. And the kids picked up on this clue. And then they noticed a really small print down at the bottom of the letter. They've got this sentence here. I have no idea what that says.
Is that Latin?
Well, let's check this out. So Lenore says, "Hey, this is kind of interesting. I've never seen this before." Her great uncle had written the letter to her Aunt Agnes. And the clues in the letter must be some kind of a cipher. Maybe this is a Caesar shift. And I don't know if you guys have ever heard of a Caesar shift. If anybody's heard of one, I'd love to know that. Put that in the chat real quick. A Caesar shift is basically we take letters in the alphabet and we hide messages by taking letters in the alphabet and shifting them and making certain letters correspond to other ones. So example, maybe the number of letters between R and E would determine how far that shift was. And so all of the letters in the alphabet are shifted that direction, and you kind of wrap around the ones from the end and bring them up to the beginning. So the shift looks like it's about 13, Bobby exclaims. And so if you guys can decipher this, I'll give you just a second or two to decipher this sentence here and see if you guys can come up with what this Caesar cipher might have been. While you guys are working on that, I'll continue to set up the situation. So the kids, they worked it out. They've kind of got an idea of what the cipher was, and they went upstairs and they happened to find a map of the farm on the next page. So this is the family farm. You notice a little house down there in the corner, and some of the structures around the farm were there. And they also found, not along with that map, they found a grid of numbers and a little template with some holes torn in it. So imagine like a little sheet of paper with some holes punched in it in these very specific places. And next to those holes, there were actually some letters too, which is kind of interesting, kind of an interesting way to think about that. So has anybody figured out the cipher yet, Eric?
Not that I've seen in the chat, not just yet.
Well, Eric, did you know the author of that book?
Well, a lot of people in the chat did know that, and they found out that it was Edgar Allan Poe. And
what was probably the most well known of his poems?
Well, I know in a lot of high schools they'll teach the Raven.
Yep, the Raven. Well, I've got news for you. I'll decipher this for you. That sentence there says the black bird in the book of Poe. And so the answer to the cipher that we were interested in is Raven. All right. My fingers don't work. I can't type, but the answer is Raven, and we'll submit that. And that lets us into the next step of the problem, which is kind of cool. Like we couldn't pass that page until we got through that. So, all right, good job solving the cipher. And here's the little template we were talking about and the grid of numbers that the kids found. So I'm going to just drop that on there. Now, one of the things that was on that piece of paper, there was another clue. In fact, I skipped over it. It said that they needed to turn, here it is, according to the clock, 0, 90, and 270. Now, I don't know very many clocks that have 0, 90, and 270 on them, but those sound like pretty familiar angles to me. So let's play with the angles. So here's the numbers. Here's the 4 numbers. And if you guys are going to play along, I'd encourage you write down these numbers and letters because those will be important in just a second. So 4 and A, H and 20, M and 2, T and 10. Okay, so that's 0 degrees, right? That was the top. So 90. Let's a clock rotates to the right, counterclockwise or clockwise rather. So rotate. Yeah, not counterclockwise. That's the opposite of what a clock does. So let's rotate this to 90 degrees. All right. So there's our 90 degrees spot there. Okay, so write these ones down. 18A, T, 26, 16M, and 3H. And then let's see. So 90, 0, and 270. Now, if I hit rotate 270, I'm thinking it'll go all the way back to the original position, right? So if I go all the way to 270, that's what I had before. So that isn't what I wanted. So if I had 90 and I rotate another 180, that'll give me the 270. So that's perfect. All right. So here's our last one. So I have A6, T1, M10, and H9. All right. So there are the numbers that we have. I'm not really sure what we're supposed to do with those, but let's keep moving. That night they slept, and the next day Bobby commented to Allison, "Hey, did you know the sides of the map are also numbered?" I don't know if you guys picked up on that just a minute ago, but if you look at the map, it actually has some numbers down the sides here. So Bobby says, "Hey, maybe this is like XY coordinates." But we got all these random scrambled numbers. What do we do with them? Allison says, "Hey, I bet they spell a word." Did anybody pick up on what that word was?
I'm watching the chat, not yet, but a couple of students did figure out the Raven. They figured out it was Raven, and a student by the name of Wing figured out that the 0, 90, and 270 were probably degrees. So these students are pretty sharp. They're on it.
That's awesome. That's awesome. Well, I'm going to give them just a second thinking about this cryptic piece here, and maybe they've had a chance to think about what that looks like there. I'm thinking that we do have XY coordinate pairs. And probably the first 4, maybe we can match these up and come up with it. Did anybody get that one?
Jericho's still thinking.
Still thinking. All right. Yeah. So I hesitate to take it away from them, but
no, hold on, Curtis. We have an answer. Lisa Robner said math.
Ah, yes, MATH. Right.
And so did Carlos and Madison.
Math. So if, since we figured out the words are math, then probably the first letter of the word is probably assigned to X1, the second one to Y1, and then X2 and Y2. So let's actually do that. Let's assign those guys out there. So what you're going to find is that you're going to want to plot those out. And I'm only going to do a couple of these. I've got a page here where you can drag the points down. And so you should probably find the first point is probably going to be, the 0.24. And the second point will kind of go along with that one. Since these two were the first ones going, we're at 1020. That should give you an idea of kind of the strategy, the direction that we were going to go with this. I'm not going to make you guys sit here and watch me pull all of those points. I'm just going to show you that we can do that. So here are all.
So Curtis, those coordinates that you were pulling in,
Uh-huh.
Those again, those were from the from that screen that you were rotating.
Right.
Okay.
So if we go back and we look at that screen that we were rotating here, this screen right here. So this was the first one we landed on, right? And so the students figured out MATH. So MA, this is my first point, 2, 4.
Gotcha.
My second point, TH, is 10, 20. And then if I rotate, whoops, if I rotate that to the maybe the third set of points, I can see that MA would give me 10, 6. TH would give me 1, 9. That would give me that second set there. So
that's tricky.
Want to, yeah, that's perfect. Thanks for keeping me honest here.
No, that's good.
So this is the set of points that we've got here, but I don't know that it really tells us anything. I haven't gotten any place with that. So it just looks like a mess of points. And I don't know if any of the students out there can see that and see if there's anything that maybe those kids could have come up with. I did put them in certain colors because they came from one thing. Anybody have any ideas of what we could maybe do? I'll let that hang there for a second. And then I'll let Bobby kind of give this away. Bobby says, man, it doesn't look like we do anything with it. It's just kind of this mess. Allison says, wait a minute, what if we connect the points from each set with a line? Seems like a reasonable idea. So here's where I want you guys to take your paper really quickly and get those points that you guys were given just a moment ago. I'll put them back up here on the screen. Take those points and actually write the equations of the lines that go with each of those sets of points. So you have the set of points 2, 4, and 10, 20. And the equation of the line that goes between 1, 9 and 10, 6. And then the equation of the line that goes between 16, 18, and 26, 3. This is where we're going to use a little bit of our algebra brain. So what I'm going to do actually here is I'm going to switch over and do a little bit of algebra. Let me get that popped up here. So here, I'll do the first one with you guys. Maybe you guys have already picked up on this. Notice that maybe this one, well, it looks like every time I do an X, it's like the double. Y is just its double, right? So this one's pretty simple. It's like Y equals 2, right? That's a pretty quick one. No problems there. The next one, 16, 18. This is actually one of the places where I wanted to make a point point. That was a good joke there. That was a math joke.
That's a good joke. Hey, Curtis, we had a couple of guesses from some students on how to make sense of the map.
Okay.
Wing was saying maybe those are telling us something about the distance. Another student, I apologize for messing up the name, Minakshi said that maybe we could connect the dots. And then Hasib said that this is probably has something to do with graphing. And then another student, Wing, was saying, I wonder if this has something to do with the distance formula. So we have some students figure things out here. This is good, really good.
Yeah, this is really good. So the distance formula is a good idea on this. Connecting the points is the direction we're going to go in this first section. We're going to connect those points with lines. And so I've got the equation of the first one. Let's do the equation for the line that connects that 16, 18 and that 26, 3. This is the second set of points. If you look at the distance or the change in y, which is what, about 15. So it looks like a decrease of 15. So we would do negative 15 divided by positive 10. So an increase of 10. So it looks like that would reduce. So let's just reduce it right away to negative 3/2. So that's the slope of this line. And then I know that a lot of students in algebra and geometry probably would take that and then they would find one of those points and try to find the y-intercept. I'm going to make a big point here, and my calculus teachers will be excited about this. My favorite equation of a line is point slope form. And I'm going to just use a version of point slope form to do this. So I've already got the slope and I've got 2 points, so I can pick my favorite one. And I'm going to just drop in for the equation of this line, x minus 26 plus 3. So anytime that you're writing the equation of a line, all you need is the slope and 1 point. As long as you know 1 point, it doesn't have to be the y-intercept. You can write the equation of a line, because you can look at this as a translation of the line to the right 26 and then up 3 that has a slope of -3/2. So this gives us a really nice, easy way to write the equation of that line. And you won't be wrong by doing that. We could simplify it and get something that's more familiar, but I love this equation of the line.
Hey, Miss Howington was all over you. She saw this coming from a mile away. She guessed that you were going to do y equals mx plus b, or point slope form. So kudos to Miss Howington. Good job.
Yeah, they are, man. They've got this. They've got this. So then the equation of the last one, I won't even make too much time about getting it. I'll just write it out for you guys. It's going to be -1/3. And then I'm going to use that same point slope form. I'm going to use x minus 1 plus 9, because that's my favorite version of these things. So we've got those equations of the lines written. So let's actually graph them. What do you think? Let's see what happens when we graph them. So I'm going to get this in here, and guess what? I've already got them typed in, because I'm a diligent student and I did this ahead of time. There we go. Got that one checked. And then let's get F3 checked. So I don't know if anybody looked at the description of this session earlier, but it did say something about triangles. And so this is kind of the direction we're headed. So look at this. We've got a triangle. We got a really cool thing. So this is kind of a cool development in the story. A triangle might make some sense. So let's keep following what the students do. So they've made that triangle now. And they determine a triangle. So anytime that I have a triangle on a piece of paper and it's on a graph paper, I probably want to find out what those vertices are, right? So Eric, we could ask these guys to do some really cool algebra and get them thinking about solving those equations, those systems of equations in each one of those places. So I think that would be a fantastic way to do that. So let's go back and look at our scrap paper here, because that's going to be important in just a second. So we found the triangle, but we need to know where the vertices are. Now, because I didn't want you guys to have to watch me write all this algebra out, I went ahead and did the work ahead of time. So I'm thinking hopefully you guys have a little bit of time there to start working on this, and then you can check your answers against mine here shortly. But I'll just do the first one with you and show you where that one should be. And then we can look at the others if you want to in just a second. So the first thing is I want to look at where y equals 2x is intersecting my equation of the line -3/2 x minus 26 plus 3. So just for reference, I'm going to be looking at the bottom right-hand corner, or sorry, the top right-hand corner left. This is my left right here. My left. I'm working on that. The top left-hand one up there. That's where I'm looking for. All right. So these two, we're going to set them to each other. It's a simple substitution, right? Because I've got them both in y equals form, so I can just set that up. And then I can just work out the algebra. I can do a little bit of distributive property and get this thing worked out to 7x is equal to 84, which gives me x is 12. And then because I've got this really nice, easy 2x one in here, I'll just double that and get my 24. So the first intersection point is at 1224. And hopefully maybe some of the groups had a chance to work out some of the other intersection points, because I'm going to show you guys a nice feature of the calculator to cheat here just a little bit. Not cheat, verify my solution.
I had a question on the chat. Leah Anderson was asking if this was a 30, 60, 90.
Ooh, that's a really good question. And I'll be honest, I don't know the answer to that. I don't believe it is a 30, 60, 90 because these two are not quite perpendicular right here. But that's really a good thought process on figuring out, well, maybe we could figure out some things about this based on 30, 60, 90. That's a really good idea. All right, so I'm going to get those intersection points in here. Before I do that, I'm going to hide some of this other stuff because it gets a little crowded down in here. So I'm going to hide all of these points, make sure that these guys are gone. Plus I'm giving you guys some time to do your algebra that you need to be doing to find the intersection points. before I reveal them to you. So I'm going to use the menu key here. Go into geometry because that's a really nice handy piece that we have there, and look for the intersection points under points and lines. So I'm going to find the intersection between, I'm going to find the intersection between this point and this line there. So I've got one, that's my 1224 that I just solved for a moment ago. So I know I did my algebra right there. Hopefully some of you guys maybe picked up on this one and found this, this solution here to be 28,0. And then maybe some of you guys worked out the intersection between the 2x and the -1/3 graph there and found that point to be 4,8. So we now have these 3 points, 4,8, 1224, and 28,0. So those 3 points are helpful, but they haven't really got us to the solution yet. We're still kind of in this, okay, we know this triangle. Anybody have any ideas about what these kids are going to have to end up trying to find?
So far, yeah, so far we have
or outside the triangle.
Lisa Robner said that no opposite reciprocal slopes.
Ooh. Oh yeah. Okay. Yeah. So when on the question of the 90, 30, 60, 90, we didn't have any opposite reciprocal slopes. So we knew that none of the angles were 90 degrees. That's a really good observation.
Ms. Howington said that I think she's letting her students know that you used substitution in your math. And then Kimberly Keeler said the slopes would have to be opposite reciprocals if one of the angles is 90 degrees.
I love it. I love it. These guys are right on top of this stuff. And in fact, that opposite reciprocal thing is going to come up right now. We moved on. So Bobby and Allison were in math class the next day. And they figured out that they have a triangle, but they don't really know what else to do. And Mrs. Clem, anybody pick up on that name there? That's an important name from Edgar Allan Poe stuff. So pay attention. All right. So Mrs. Clem was saying this. She said, today we're going to be investigating whether we can find a point that is equidistant from 3 vertices of a triangle. What? Equidistant from 3 vertices of a triangle? Hey, we have a triangle. We have 3 vertices. Maybe this could be something that could be helpful. So could you guys maybe take a second and think about how that might be accomplished? Thinking about how in your groups this could be done. Finding one point that's equidistant from 3 points that define a triangle. Think about that for a second. I'm going to give away a little bit of it. I know we have a 20-second or 30-second delay, so hopefully they've had a chance to think about this for a second.
We had Shreya, Shreya mentioned that now we can calculate the distance is a question she was asking. Now we can find the distance of all 3 lines. Yeah,
we could find the distance from all those 3 lines.
Right.
Something like that. That would be an interesting thing to try to tackle. So in the math class, it turns out that Mrs. Clem started talking about this thing called a perpendicular bisector. And if you break that word down, a perpendicular bisector takes a segment or 2 points on a line and divides that segment into equal pieces, so equal distances. That's where that distance formula thing could come in to play. That would be very handy in finding the midpoint between two points, all right? And then we're gonna make a perpendicular to that. So not only are we gonna find that midpoint, not only are we gonna break that segment in half, but we're also going to make a perpendicular line to that. So that's going to be kind of an interesting piece. Now, this is kind of an interesting realization that Allison has. She says, I remember that any point on a perpendicular bisector of a segment is equidistant from the segment's endpoints. In other words, if I take a perpendicular bisector, if I take this segment from A to B, and I divide it into halves where E is the midpoint, so now I have this equal length and that equal length, okay? AE is equal to EB, okay? then if I make a line that is perpendicular to AB that goes through the point E, all of the points on this line, any point C that I want to drag this to, will be equidistant, the same distance from A to C as it is from B to C, which is kind of an interesting thing. Like, that's really cool. So the perpendicular bisector defines the set of all points equidistant from 2 points. You think that might be kind of interesting or important in our story? I don't know. Let's keep trying. So we're going to keep navigating this and keep moving. So Bobby replied, hey, so if we construct perpendicular bisectors along the segments of this line, I want you guys to take a second and think about the equations of those perpendicular bisectors. Whoever mentioned the opposite reciprocals a moment earlier, that is going to come into play very, very importantly shortly. Okay, we're going to navigate over here, and I'll give you guys a little bit of help. I'll give you the midpoints. You don't have to figure out the midpoints on your own. You guys can come up with, here's the midpoints, but that opposite reciprocal is very important.
Yeah, Curtis, there's some questions.
Okay.
They're trying to figure out if we're looking for the circumcenter, the center, the centroid. Shreya mentioned that, so if AE equals EB, and Wing said, and AC equals BC, I think they're trying to work it out here. They're trying to figure out what we're actually looking for within the triangle.
All right. So we've figured out, these guys have figured out that, you know, within this triangle that we're looking at, we're going to try to find some point. And the person who mentioned the circumcenter, I think that could be the direction that we're heading, but we're going to find out. We're going to find out. See, we'll see what this is. So let's go ahead and use that. Let's go ahead and use what they just discovered for us. Let's go ahead and navigate to those perpendicular bisectors that those guys are creating, the equations of those lines. The first one is going to be going through the point 2012. And so we'll need to make sure that we have that point 2012 in our minds. And then the next one, 16.4, and the last one's going to go through the point 8.16. So I'm going to flip over here to this graph, and we're going to go ahead and add in those perpendicular bisectors. So let's do that really quickly. I'm going to hit Control G, and I'll just do the first one. So if we're looking at this equation of the blue line here, which is, by the way, y equals 2x, right? We're looking at y equals 2x. So something perpendicular to y equals 2x would have a slope of -1/2, right? That's that opposite reciprocal that somebody mentioned earlier when we were talking about the perpendiculars. And then it's going to go through that point 8.16. And so I've written that equation in point slope form. And let's just go ahead and graph that one and see if we see anything. Doesn't really help me that much. So let's add another one. Let's put in another one. So thinking about this equation here that had the slope of -1/3. So this black line that's going through the bottom here. If I were to find a perpendicular to that, it would have a slope of +3, right? And then I told you the midpoint was 16.4. So it's going to go through that point 16.4. So let's add that one to this. Ooh, Eric, guess what? Those two intersect. I wonder if they intersect at an important place. It's kind of interesting. Let's go ahead and add the third one. Let's do that. Let's add the third one. I think I've probably belabored this long enough, and now we've probably got some students commenting that, hey, those three are going to intersect in one location. Does anybody have the name of that location for me? While I find the intersection of that point. So you can set up and solve the system of equations of those again. We could definitely do that. In fact, I'm gonna do that. I'm gonna show you another little piece of the calculator. So let's let's go ahead and insert a calculator page. So I'm going to find the solution. I'm going to use the numeric solver here and find the solution for where F1 is equal to F2. And I've never done this. This is going to be a live test. I've never done this with functions before, so we're going to try this. So we're going to solve. Actually, I wanted the numerical solver, not the numerical solver. So we're going to do numerical solve. So we're going to do nsolve, and we're going to say F1 of x, oops, is F2 of x. No, it wasn't F1, was it? It was F5 and F6. Never done this before, so you guys are getting to see something live. If I make a mistake, I apologize, and we'll just look at that. And I don't know if I have to give it a number. I think I do. Let's just try. Oh, I didn't give it a boundary. Okay, we're going to do solve instead because I know that works.
Hey, while you're doing that, Curtis, I want to give a shout out to Lisa Robner, who guessed correctly that you need a perpendicular line to each side of the triangle that all intersect. And then she said that actually you really only need 2 of these lines because the third one will intersect at the same point.
All right. I shouldn't have tried that live. I should have tried it beforehand. And I didn't. All right. So we're going to find the intersection using the geometry tools. I wanted to do it with algebra, but I didn't prep that. So we're going to do it with geometry tools. All right. So I'm going to find the equation of this line here and find the intersection there. And that whoever mentioned that we only need to find 2 of those instead of all 3 is absolutely correct. We really only needed those 2. But just to prove the point that all 3 of them intersect in one location, I wanted to go ahead and draw that in there because I think that's kind of a cool and an important thing. And the person who named this as the circumcenter is absolutely right, because what this point actually is, remember that what we were trying to solve earlier was the point that is equidistant from those 3 points on the triangle. And the cool thing is if I measure the distance from, say, this point to that point, I get 14.6 units, right? And if I measure the distance from this point to that point, I get 14.6 units. Isn't that cool? And if I measure the distance from here to here, that's also cool. And remember what this whole thing was. When we decided that a perpendicular bisector defines the set of all points that are equidistant from 2 points, that is equidistant from the ends of the vertices of this triangle or ends of that segment, this green line defines all the points in the universe that are equidistant on this plane anyway from 28, 0 and 4, 8. And if I do that again for this one, 4, 8 and 12, 24, then this orange line and that green line define the set of all points equidistant from those 2 and from those 2, and they share one common point, which means this one is equidistant from all 3 of those points. It's kind of a cool way to work this out, right? Kind of a neat way to come up with this. So now we found this point. So what? Well, we've got a little bit more time, right, Eric?
Yes, we do. Absolutely. Keep going.
All right, so let's keep moving. So we found this crazy point. The kids solved for the point. They found out this point. So let's now we've got this piece here. The kids go out into the yard. They find the coordinates of that point on the map, and they take their shovel with them. And so let's put in those points. 18.3. And what was the other one?
Don't remember.
10.9.
0.9. Yep.
Okay, so let's put in 10.9. And we're gonna dig and dig and dig. Wait a minute, what's this? Hey, it's an old wooden chest. This is kind of cool. So in the backyard, there was an old wooden chest. Now, there's this key. I wonder where the lock is. Now, one of the cool things about this lesson, and I love the fact that we had an opportunity to put some geometry to use our solving systems of equations, finding perpendicular lines, certainly finding perpendicular bisectors, both by construction. If you wanted to, you could get out your compass and straight edge and make perpendicular bisectors, or you could go in and come up with those perpendiculars by finding the midpoint, and then finding the equations of those midpoints, using those opposite reciprocals and point slope form. All kinds of really good ways to tackle this particular problem. But we didn't talk a ton about all of the cipher solving, right? So there's some more that we could do here. And in fact, one of the things that Dr. Strauss actually showed us and talked to us a little bit about was ways to encrypt and decrypt messages and things. And so, Eric, we actually put in this lesson, we put in an encryptor and a decryptor, which is kind of a fun way to end the lesson, right? So there was more exploration that we could do. So Allison's mom was really proud of the kids, and wanted to give them maybe a modern demonstration of encryption, you know, beyond cipher solvers and little things that way.
Hey, before you do that, and I know everybody wants to hear about that, a couple of questions for you.
Sure.
To finding the location of the chest, is there a difference between how you would do it on an 84 versus how you would do it on the Nspire?
So on the 84, it's the same kind of thing. You can find the equations. I should have had that pulled up. I can find those equations and then use either the numeric solver, which I didn't do a very good job of demonstrating, and I apologize. I should have been prepared for that, and I messed that up. But then you could also do using the equations on the graph and do the intersection tool on the graph. Now, in the 84, there isn't a geometry version of this, which gives me the points and lines. On the 84, and I'll demonstrate the equivalent tool on Nspire because it works the same way on 84. On the 84, there's actually underneath of the calculations menu. So if you press second, and I guess that's, what is that, F3? I don't have here's my 84. It's second and F4. There's a calculation menu. Second and the trace button. There's a calculation menu, and that gives you the opportunity to calculate a zero, a minimum, or maximum, or this idea of an intersection. Now, what's different is when you do the intersection tool, it's going to ask you for one graph and then a second graph. So I'll choose the green one and the orange one here. And then it's going to ask me for a lower and an upper bound. In other words, I need to bound the intersections, the space where I want to see where there's an intersection. So I'm going to click and make a lower bound, and then I'm going to drag that over and do an upper bound. On the 84, some of you guys might be familiar with it being equation 1, equation 2, guess, or sorry, lower bound, upper bound, and then guess. That's going to be kind of the same process that we would use here for this. And so there's our same intersection of 18.3, 10.9. That's a really good question, Eric. Any other questions on that?
Just a lot of comments. Shreya was saying, hey, this is really cool. Wing was saying, now they know the destination. And by the way, Wing got a shout out for having a big brain. So I want to make sure we mention that.
All right. That's awesome.
Yeah, congratulations.
Well, I'm telling you what, man, Eric, I've been super impressed with the kids on this lesson so far today, because, man, they've nailed down, they've known exactly where I was headed this whole time. Every single one of them is like, well,
yeah, they're pretty.
And now you're going to do this. I can't verify the algebra. I can't verify that they're doing all the algebra. They certainly know the geometry, and they know kind of the strategies of what we're going to do in this piece. So I want to kind of wrap up our session with, unless there's more questions, I want to do a little bit of a demonstration and kind of give a demonstration of how this encryption piece works in the last part of this. No, so any more questions?
No more questions. Ms. Howington just verify that yes, the perpendicular bisector's point of concurrency is the circumcenter equidistant to the vertices.
Oh, you know what would be really cool? Before we do the, while we're still talking geometry, let's do one more thing.
You're going to leave them in suspense as to what we're going to do next?
Yeah. While we're still talking geometry, let's do this. So because we talked about this being the circumcenter, we talked about this being equidistant from all of these things. I bet you guys can decide what the radius of the circle centered here that intersects those 3 points ought to be, right? Anybody have a guess?
So Sharia says that so the circumcenter is equidistant from all the 3 vertices of the triangle, correct?
That's exactly correct.
Yep.
So I'll show you what we're going to do. Check this out. I'm going to make a circle. Bam. Now, is that not cool or what? Like, I know the first time I saw this, I'm going to change the color of that. The first time I ever saw that, I was like, man, that is just so cool that when we find that, and I know we talk about attributes. I want this. I know we talk about this in our geometry classes and we find them, but when we did it in this context, it was kind of this really cool kind of aha moment that, oh man, we did all of that work and check that out. That circle right there is exactly what we defined by getting those 3 vertices and then finding that perpendicular bisector, all the perpendicular bisectors, and then the circumcenter. That was really a neat realization for me anyway, to see that. So now it's really nice. We can see maybe what the great uncle was trying to do and using his mathematics to hide a piece of treasure, the family treasure, and who knows what that key goes to. I don't have any idea what that key goes to at all. So, but it's kind of a cool piece that worked that way. All right.
Yeah, dead center of the circle. That's really neat.
Yeah, just that it comes out to be the center of a circle. It's like, what? Oh my gosh. And the radius of that circle really is 14.6 units, which is cool. Yep. All right, so let's do this demonstration, and then we'll kind of wrap things up here, unless we have more comments, which is great. I love the comments, by the way. I'm loving the comments. So on the next day, there's an encryption demo, and the kids got a little bit of time to play with this. And so what we're going to do is I'm going to encrypt a message, and so we actually have the ability to encrypt and decrypt a message here. This is not ultra fancy, but inside we're going to give it a 4 to 12 digit, and this would be what we would call like an encryption key. In other words, this is the thing that you might give to both team members or both people at both parties in your group, so that they'll know how to decrypt the message. So Eric, give me your favorite 4-digit number.
Let's see, 1776.
1776. That's a good number. Anybody know what that number is? Type that in the chat. And then we'll type in our message. Our message might be independence, to go with Eric's little theme there. All right, we'll go Independence Day, just to give us a little bit more text to. So now we've got this message, and there's our encryption message right there. So, and if you guys want to, I'm going to have to write this down. That looks like QVLMX. LMVKM space LIG. All right. So this is our message that we encrypted here. I don't think I can copy that, so hopefully I typed it down, or I wrote it down right on my.
We'll find out.
So now let's go back and let's go back and see if we can get that Independence Day back. All right. So we're going to use the same decryption code. So we're going to use QVLMVKM space LIG. And I don't know if anybody noticed something. Maybe somebody did. Did anybody notice the relationship that's really true, really apparent here in the letters that are being typed out? It's like
It seems like there's a bunch of letter M's.
Yeah, there's a lot of letters being repeated a bunch. All right, so let's see if anybody comes up with what that was actually doing. Hey, we did get it. Did anybody notice the correlation between, you know, this idea that we have this letter M being repeated a bunch in here? 1, 2, 3, 4 E's, 1, 2, 3, 4 M's. Hey, Eric, it looks like this was a Cipher cipher.
Yeah, I think you're right.
I think it was. And in fact, if we really wanted to get nerdy about this, we could probably figure out the letters between E and M. And we could probably figure out that that would be the remainder of dividing 1776 by 26. How many letters are there between E and M, Eric?
Between E and M?
Yeah, between E and M.
I'd have to use my fingers. I don't know. 13?
I think you're right. 1776, comma 13. There's 8 letters between E.
Ah, okay.
Right? There are 8 letters between E and M, and that's exactly what we had. So if you look at that, if you look at the way this cipher works, this 1776 encryption key basically gives us the number of digits that we would shift this. Now, it would be pointless to shift every letter in the alphabet 1776 spaces, right? It would be easier to figure out how many times 26 goes in there and ignore all of that and then look at the leftovers and look at the remainder, because that's how far it would actually shift. And then we can use that to shift our set of letters. So this is kind of a cool way to do an encryption, way to kind of randomize the letters and use a Cipher cipher, which is something that's figure outable, but at least something that's interesting and can be done. And hopefully you guys enjoyed the lesson itself and some of the questions that we had involved in there. Any other further questions or comments, Eric? Anything coming up?
Yeah, we had some people that guessed correctly 8 letters, but everybody got it. They understood that M was equal to E, and so from there they can figure out, you know, the positions of the other letters. So back when I was in school and we didn't have cell phones, we used to write notes on paper to one another, and we'd fold the notes and we'd try to get it to the recipient without the teacher detecting us. Sorry, teachers. You know, I know.
Wait a minute. You mean you used to do this like before like cell phones and we could just text each other? What are you talking about?
Yeah, we used to write on paper. It's amazing. And we would fold it up and send it to one another. Man, if I would have known about the Caesar shift back then, the teacher that caught my note wouldn't have read it in front of the class. She wouldn't have been able to tell what it meant. So I think this is great. Maybe
you would have gotten some credit for being kind of smart in hiding your message that way. Maybe
right,
maybe there would have been some credit given.
Yeah, if I would have known about this encryption stuff back then, then you know, that would have been pretty cool. But you know,
that's pretty awesome.
The whole Edgar Allan Poe thing's really neat. If you guys listening in get a chance to do a little research on Edgar Allan Poe, he was a weird dude. Okay, so just get that out of the way. But he was really into like cryptography, and you know, he did a whole bunch of newspaper editorials where he would challenge the public to challenge him on different ciphers, and every single cipher that he received, he was able to solve it. So the guy was pretty neat, really creepy, weird, but really into this cryptography thing. So activity was a little bit of hat tip to some of the cryptography that Poe did back in the day. So anyway, Curtis, a lot of folks are saying thanks for the lesson. You know, someone's saying that yes, yeah, Olivia correctly pointed out that Edgar Allan Poe married his first cousin, which is where the Mrs. Clem came in. So
nice, we got one.
you guys figured that out, which is cool. But yeah, a lot of cool stuff. And I think some folks are recommending more live lessons. So appreciate that. And Curtis and I and others will keep doing these things. If you guys
happy
feedback, let us know. What about you, Curtis? Anything else on your side?
No, I didn't have anything else on my side other than there are some more fun and interesting things in that lesson that I did not show, that I did not showcase. So I would encourage anyone out there watching this that has access to the software, in which they still do have access to the software really quickly. You can still download the TI software for free for 6 months. You can still go to our website and check out the COVID support and download that software right now. I think that would be an important thing to do. Just to, if you want to, for nothing else, during the summer, if you want to go and play with this lesson, it would be kind of a cool lesson to download. So if you go to the activities and go to STEM activities and look for STEM Behind Hollywood, you will find our resources here. In this particular lesson will be a part of the STEM Behind Hollywood series of lessons under cryptography. But I would encourage you to go in and download this lesson and explore, because even though you know the solution to the problem, there are still several things in there that are of interest and hidden, and I encourage you to go dig.
Yeah, we didn't reveal everything. So a little carrot for you guys to go back and try to figure out what we didn't reveal.
Yep, I think that would be it. Well, Eric, unless you've got any more questions or comments, I think we're probably good to wrap up.
Yeah, I think so. Just a couple of folks noted that, yes, Edgar Allan Poe's cousin was 13, very young. Things were a little weird and different back then. We don't generally do those kinds of things these days. Colin made a good observation in the word independence that many of the repeated letters in independence have a lot of repeated letters. And so I think Colin might have been going to pretty much the concept of frequency analysis. So back then, you know, a lot of words had the same kinds of letters. So the letter E pops up all the time. Just about every word you can think of has a letter E in it. And so when you see a series of words, chances are the letter that pops up most is probably going to be a letter E. And so, you know, that's a way that Poe and others figured out the cipher shift. How they shifted a bit was looking at the frequency of letters that pop up. So cryptography is really cool, you guys. You know, look into it, check it out, and Curtis, make sure you unshare your screen to say goodbye.
I will. I'll do that. I just wanted to kind of comment to piggyback on that, though, that yeah, even nowadays, you know, that repeated lesson, that repeated letter and the frequency analysis is still a big part of what happens. Nowadays, it's not so much letters as it is prime numbers and working out really big, huge prime numbers and the way prime numbers work together. But there's a lot of really interesting, really cool cryptography that's happening out there. And I would highly encourage, just like Eric did, you guys that find this interesting to go ahead and
yeah. The other thing too, one more point before we say goodbye, is that everything that Curtis showed you today, and when we got into this whole encryption decryption thing, computer code, you guys know this, it's the same kind of idea. Computer code, if a company doesn't want you to look at their code and understand how they coded something, they encrypt it. And it's very difficult for you to try to decrypt it. You have to know kind of what the key is to be able to do that. And so everything that you're learning today is in practice today in computer software. So kind of neat. It's, you know, this stuff's been around for a long time and it's still being used today.
It's way cool.
Yeah.
All right. Well, thanks, Eric, for having me, and enjoyed it. So I guess we'll sign off.
I think so. And don't forget, we have some more live lessons next week. So be sure to check out our YouTube channel, TI Calculators, all one word. And thanks everybody for attending. Hope you got something out of this, and have a great day. Have a great weekend.
Bye, guys.
Bye-bye.